So I've been having a lot of difficulty with problem 19 in chapter 7, part B.
Okay. Are you going to take the P exam?
I'm planning on taking that at some point this summer. So,
Okay. Well, I'll just tell you, like, I think you know enough stuff to go take it at this point. I mean, you've read past, I think, far past what you would need, but I don't even think on the test that they're going to ask you anything about limit theorems per se. So, um, 7.19. Those a certain region, is that the one?
yeah.
A certain region is inhabited by R distinct types of a certain species of insect. Each insect caught will, independently of the type of the previous catches, be of type I with probability pi, where the pi's add up to 1. Okay? Compute the mean number of insects that are caught before the first type 1 catch. All right.
So, part A was pretty simple.
Did you
I
just
really
do
just had to use the geometric.
a geometric with a proportion of success P1 basically?
Yeah.
Yeah.
So, the problem was in part B when it asks you to compute the mean number of types of insects. Um, So basically I let y be the random variable, meaning the number of types before type 1, with y sub I being the indicator variable, meaning that the ith bug was caught. Um, then the expected value of y is just basically the sum of the expected values of the y sub i's from 2 to r.
Okay. So you let y be the number of types caught prior to type 1.
Yes.
And you let y, tell me again, y sub I.
Means the ith bug was caught before type 1.
I see. So y2 plus y3 plus ... plus yr,
Yeah.
where y I is equal to 1 if type 1 or if type I caught before type 1, right?
Yeah.
And 0 otherwise. All right. So you're saying that what you want is the expected value of y,
Yeah.
and
Which is
that's just
just the sum of all the expected values.
right. So it's going to be sum I going from 2. Oh, wait, yeah, 2 to r, the expected value of yi. That's
Yeah.
it. Yeah. Yeah. Okay, cool. Um, type I caught before type 1. So basically, isn't this, aren't they going to be, well, I mean, the only difference is you have different probabilities for the different I's, right?
Yeah.
But other than that, the solution's going to be the same for each one of these expected values.
Yeah.
You're
The
out
problem
them.
is I can't figure out how to calculate the probability that it was caught before type 1.
Yeah. The probability that type I is caught before type 1. So basically, hmm, yeah, the problem is you have, okay, so each bug catching sequence basically is going to look like, you know, a bunch of numbers, okay? And then you have a 1 kind of finishing this thing off. Yeah?
Yeah.
And if, let's just say, and we're just going to use the actual type numbers to represent that I caught this bug, okay? So if type I was caught before 1, we need to see greater than or equal to 1, greater than or equal to 1 I here, right? Does that make sense? So like if I was going to catch type 2 before type 1, oh, and by the way, there's, and incidentally, in these first however many slots, there's no 1. Does that make sense? So this 1 is the first to appear. This is the first one. Okay?
Yeah.
First one to appear. So, how could we here's the question number 1. How many sequences are there? So suppose I have, so here's a question that we need to answer. How many length in sequences of sequences taken from this set, okay, have so by the way, we want these sequences to be with multiplicity, right? So actually with repetition allowed. Okay, have 1 in the last slot only. Okay, and I somewhere before. We need to be able to count this. We need to be able to count these sequences or else we're going to be in trouble. You know what I'm saying? If we can't count those, we're in trouble. Yeah? Okay. So, well, that makes me think that basically that's just an n-1 long sequence. Okay, so this is the number of n-1 long sequences formed from the set without 1, correct? Formed from 2, 3, all the way up through R with repetition that include I. Does that make sense? Because I just exclude 1, that's going to be last. Yeah?
Okay.
That number. Think about it for a minute. How many bad sequences would there be, Matthew?
Um,
What would a bad sequence be?
it would basically be any permutation that doesn't include I.
Right, anything that doesn't include I. So basically that means I would just be, I wouldn't, it's almost like I would pretend I didn't have I. So I would be, right now, I mean, there are R-1 elements I'm going to build this n-1 sequence from. Okay. So essentially, it seems like you should just do the total number of these minus the bad ones. Okay. So look, it seems to me like you should just go R-1 raised to the
n-1.
R-1 to the n-1 minus what?
Would it be R-2 to the n-1?
Yeah. Okay. But the problem is, right, so that's the total number of them. Okay. So that's kind of a first step, is we know how to count the total number of these things. And incidentally, the length of these, right, the length of these could be anywhere, n could be bigger than or equal to 1. Does that make sense? Because technically speaking, this experiment could go on forever. Yeah. Like you could just keep you're going to keep going till you like catch a bug of the first type or something. Okay. That's kind of like, we got set up to do that anyways before, because in the first part you said the answer was the geometric, right?
Yeah.
But the problem is, it's not enough to just count the total number of these things, because I also need to know which bugs I caught, because the probabilities of catching those bugs is different for each one of these. Does that make sense?
Yeah.
Okay. So so this is, I have this is the thing that gives me the total number of these bad things. But I also need to know, okay, for a given one of these sequences, we've at least counted the total number of them, but for a given one of these sequences, I need to know how many bugs of each type I caught. Yeah?
Yeah.
Okay. I think we can do that too. So that's kind of a second part for this count. And the reason I need to know that, Matthew, is because they occur with different probabilities. Yeah. So how many of these in long sequences, how do we say this? Have into type 2, N3 type 3, ... in R type R. And what has to be true about N2 plus whatever? What has to be true about these things?
Those are the probability of catching each bug, right?
Well, no, that's the number,
Oh, okay.
the number of each type. So what does that have to add up to total?
N-1.
Yeah. And what has to be true about these n's, I guess? So like we want ni to be greater than or equal to 1, right? Because that's telling us that we have at least one of type I. Does that make sense?
Yeah.
Well, that's an annoying restriction. So one thing I could do is I could kind of like replace well, I don't know. So maybe I'll put M1 or like M2 equal to N2. I'll put M3 equal to N3. Dot. Okay, but MI is going to be different. MI is going to be NI minus 1. I'm just going to shift that down by 1. And MR is equal to NR. So all of these M's are just the same as the N's, except for the ith one, I'm going to shift down by 1. Then let me ask you, Matthew, what would be true about the sum of these new variables? Right now I have MI sitting here. That would be
Would equal N-2.
Yeah, N-2. And now the only restriction is that the MJs are bigger than or equal to 0, right? I mean, the MJs are bigger than or equal to 0. And by the way, they can't be any more than N-2, but that's sort of forced by requiring that they're all bigger than or equal to 0 anyways. Okay? So how many of those sequences are there? What do you think? Isn't this kind of like a Mississippi problem? I have M2 of one type, M3 of another type. And basically it's like going to be, I'm going to see a whole bunch of 2s potentially. I'm going to see a whole bunch of 3s potentially. Yes.
Yeah.
3 3s, M4 4s, etc. Doesn't it, remember the Mississippi problem where we kind of said, how many ways are there to arrange the letters in the word Mississippi? Yeah.
Yeah.
So what is that? So what's the number?
So it'd be R-1 factorial over.
Actually, it's N-2 factorial.
Oh.
Because that's the total number of letters, yeah?
Yeah. Divided by the factorial of each of the individual M sub j's.
Right. And that's actually something called the multinomial coefficient. Okay. And then what would be the probability? Yeah. What would be the probability, so therefore, what would be the probability of this particular sequence occurrence? Probability of this, or of this sequence type is equal to, well, it's going to be the total number of them. I know how many type 2 I caught. I know how many type 3 I caught, etc. Yeah. But it's this. But then I have to account for the probabilities, yeah? So what
Okay.
probability is going to be?
So it would be each p sub I raised,
Well, there's P1. P1 is raised to the 1, right?
yeah. So each of the other p sub i's would be raised to the m sub j, right?
Yeah. There's one that would be a little bit strange. PI. I'm getting a little bit nervous about PI. I feel like that should be raised to something different, shouldn't it? Shouldn't it?
Wait, why?
Would it just be MI? Well, because the reason I'm saying is NI minus 1. Oh. Well, maybe not. I don't know. We can think about that later. I mean, I'm just worried that there might be some slight tweak that might need to be made here, but okay, so then it's like PR to the MR, right? And then what would be, so this is the probability of a particular bug sequence where we get bug I before bug 1, correct?
Yeah.
We just computed right here. And the thing is, I would have to sum this thing up, right? I mean, so what would be the total probability? Probability that bug I caught before bug 1. What's that going to be? How could I take that thing we just computed and get it? What do you think? Wouldn't it be a sum of some kind?
Yeah. Would it be from 1 to n minus 1?
So I think, so we would go like the sum for, I mean, n, okay, we would have to sum over for n in some range, n greater than or equal to something. Then there would be an inner sum also, wouldn't there? I would have to also sum over all possible m's. So m2 plus dot 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 plus m r equals n minus 2 with the mj's bigger than or equal to 0. Okay. And you would have this thing right here. Right? That would be the sum end sitting right there. But what would the range of n be?
It would be 3 to infinity.
Is it 3 or 2? Be n big.
Oh yeah, sorry, I forgot you
Yeah,
made all the m sub j's greater than 0.
yeah. Does that make sense? I mean, that thing looks horrible, but that's at least the probability that that happens, yes? I think there's actually, I mean, didn't they have a formula for the multinomial coefficient in the text somewhere? Or the multinomial distribution?
Yeah, but I don't remember what chapter that was.
Yeah. We actually wrote down the multinomial theorem in this class at some point, though, didn't we?
Yeah. Well, we talked about the multinomial coefficient back in like chapter 1, I think.
Yeah, when we were doing all of the counting stuff, right?
Yeah.
I'm trying to think if there's a way to simplify this sum. We actually have the sum, right? That probability is the right. So we could compute the expected value of yi, because yi is just a Bernoulli random variable. Yeah. I mean, it's easy. It's either just 0 or 1. So the expected value is just the probability that it's 1. But we just computed the probability that it's 1. It's that sum, right? You would just have to then add all of those things together for I going from 2 to r or something, right? Which looks horrible, but yeah. The multinomial theorem says that, like, if you have x1 plus dot 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 plus xr and you raise it to the nth power, what is this?
Was the sum of basically is where all the exponents had to add up to n for each of the terms.
Yeah, the exponents all had to add up to n, correct?
Yeah.
So basically, when you think of this being expanded out, you have n factors. You know, you're going to have some number of x1s, some number of x2s, all the way to some number of xr's, correct?
Yeah.
And what has to be true? So it's going to be like x1 to the n1, x2, right? This is looking sort of like what we just did, right?
Yeah.
xr to the nr. Okay, where what has to be true about those n's?
N sub I has to be greater than or equal to 0. And they all add up to n.
Yeah, and they have to add up to n. And the and the n sub i's have to all be greater than or equal. So this is a massive sum, right? It's actually an r-fold sum. That's you know, intense. But what's the number that goes in front of these? That's the multinomial coefficient, yeah? So basically you have, it's kind of like the number of ways you could do Mississippi with all of these variables, yes? You have like n1 copies of x1, n2 copies of x2, just depending on which factor you took the x1s from, which factors you took the x2s from, you're going to get all these different ways of arranging these variables. So, oops. So it's like going to be n and then like n1 dot 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 in r, yeah. And what I was hoping was, so that's what that equals. Okay. Is there, and so what I was thinking is there a way to simplify that sum on the previous slide? Because that looks almost exactly like what we had back there, doesn't it? Yeah. With one caveat, namely that P1 is like 1, but that thing can like be basically factored out or something, can it? Yeah.
Yeah.
So what I'm saying here is like this horrendous sum right here, this horrendous sum right here is just equal to this, right? It's just a sum of those things raised to the power n. So what I'm wondering, I'm just trying to explain what's going on in my mind right now. What I'm wondering is whether this sum right here, this horrible looking sum right here, right? This horrible looking sum right here, especially the one on the inside, whether that thing can be simplified significantly. Does that make sense? Like, is there a way to use the multinomial theorem to simplify that innermost several fold sum? Do you understand what I'm
So,
thinking?
yeah, would that just be p sub 2 plus p sub all the way to p sub r, all raised to the n minus 2 power?
Yeah, it seems like it might be, doesn't it?
And
Yeah,
then you just multiply by p sub 1 and then use sum from n equals 2 to infinity.
yeah, it seems like that's what's going on, doesn't it?
Yeah.
So what I'm saying is I think there's probably a way to simplify this sum. Yeah. And what would that, okay, so if I have that sum going from 2 to infinity, oh man. So say again. Okay, yeah. So that would be P2 all the way up through PR raised to the
n minus 2.
n minus 2. Oh man, are you serious? Is this thing gonna collapse? Okay, so watch. So the probability that bug eye selected before bug 1. Okay. You're saying that innermost several fold sum is just P2 plus dot 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 plus PR raised to the n minus 2, correct?
Yeah.
But then what did we have to factor out?
P sub 1.
Okay. But isn't this just 1 minus P1?
Yeah.
P1 times sum n equal to or greater than 2. 1 minus P1 to the n minus 2. Hey, what's that?
Looks like the geometric.
Yeah. Right. In fact, it starts with 1, right? It's like 1 plus 1 minus P1 plus, okay, I am nervous about something here, but I think it might be tweakable later on. So what is this? This is like, what would that be? What? Something's not right. Because what would that say this is equal to?
Wasn't that P1 times 1 over 1 minus? Yeah.
but that's just one. Okay. So where I think that there needs to be a slight tweak, and by the way, this is all going to work. Where I do think that there needs to be a slight tweak is I don't see there's something I'm telling you, my instincts were right back here. Something's weird about this. You know what I'm saying? Like something's weird about this. I don't feel like we're accounting for the fact that I appears before this. What we just computed makes sense. I think what we just computed was the probability that any sequence happens. Right? I think we just computed the probability that any sequence happens. But I think the technique that we've come up with here should work. But it's just a matter of what did we do? Where did we lose the fact that ni is equal to or greater than 1? Is there something like do I have to like account for this thing here? So let's see. The total number of those sequences. Oh, right. So the number, okay, here we go. The number of these. Oh man, we already did something like this before. Okay, so what you do is you count all of them without that restriction, namely that ni is equal to or greater than 1. So how many sequences are there with ni equal to or greater than 1? Or just with ni equal to or greater than 0, how many would there be? Wouldn't it be just n minus 1, n2, comma, dot, 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 comma, nr, right?
Yeah.
But then then I would have to subtract the bad ones. So what would I subtract? What would be the bad ones?
The ones where ni is 0.
Yeah, but if ni is 0, it's like you're just doing it with one less variable. Does that make sense? Yeah.
Yeah.
So then, so it would just be like into oh, wait a minute. Is that what I want to do? Oh yeah, that is what I want to do. So then it would just be n minus 1, and then it would be into dot, 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 right? And then like n I is 0. Does that make sense? nr. Sorry, I'm running out of room over here. Okay, so it's like I just have one less variable or something. Yeah. And then I think what's going to happen, so like that's going to be the count. Hang on a second. Yeah. So I think what you're going to have is you're going to have something like this. And it's going to be, you're going to subtract n minus 2 into dot, dot, dot. In I is 0 dot, dot, dot in R. Okay. And what's this going to be multiplied by?
Would that be the probability we calculated earlier?
Yeah, just be P1 to the first power, P2 to the N2, right? Pi to the Ni. You know, I hesitate to put Ni right here. I just want to put 0. And this 0, where is this 0 occurring? This is in position what?
I.
That's in position I. Because Ni is just Ni. Let's stop, you know, horsing around here, right? Ni is just in there. Okay. And then what is it? It's going to be P R to the NR, like that. And then I would have to add this together for what? What would have to be true about the N2 or the N's? The sum of these things is going to have to be
N minus 2. Or,
is it N minus 2? I think it's N minus. Wait, is it N minus 2? These things add up to N minus 1. You understand? So I have N minus 1s everywhere here. So actually, these should be N minus 1s. Okay. And everything, so N2, you know, NR, all of these are greater than or equal to 0, but NI is greater than or equal to 1, correct? And then I'm going to add this together for N, how large?
and from.
I think it's still N greater than or equal to 2, isn't it?
Okay.
Now, this is the correct probability. How does this simplify? Does it simplify?
Well, can we just split it up?
Probably.
Split up the sums and then apply the multinomial theorem?
Yeah, probably. But the issue, the one. Yes. Yes, we can. So, but here's the thing. So what about the sum? You know, let me just say N2 plus ... plus NR equals N minus 1. Oops. Ni greater than or equal to 1. Oops. What did I just do? I just leave? Sorry. I got booted. So I have Ni greater than or equal to 1, N minus 1, N2 ... NR, you know, P1, P2 to the N2, Pi to the Ni, PR to the NR. And the thing is, I could factor out the P1, and I could factor out one factor. So this is just one factor. I could factor out one factor of Pi. Does that make sense? So that this then becomes P1 Pi times the sum N2 plus, okay, so Ni minus 1. Plus NR equals N minus 2. And, you know, I still have Ni needing to be greater than or equal to 1. But then what would I have here? It would be like Man, is this going to simplify? I hope it does. Oh man, I don't know if it's going to. Because I don't know if that's exactly the multinomial theorem. Do you know what I mean?
Yeah.
I don't think it's quite the multinomial thing. So maybe we kind of have to leave it like that. That looks horrible though. But this definitely is, I mean, do you agree with me that this definitely is the probability now?
And then do you also have to subtract the
Yeah,
other sum?
you would have to subtract the other one, yes. And right now, all I'm doing is trying to simplify this thing. But that definitely is the probability. And by the way, the probability is the expected value of yi, correct?
So
Because
then you just take the sum of all the yi.
yeah, you just take the sum of all those. I suspect that there's a way to simplify this, but I'm just not seeing how to do it right now necessarily. So I'm gonna have to think about that. Can I think about that?
Yeah.
I mean, because that thing looks it looks it looks horrible, but it really isn't. It's just a matter of seeing how this thing is going to simplify. That makes sense. But I think
Yeah.
multinomial has to be the way to go on this one. So yeah, I see why that was a challenging problem. The first one was easy, right?
Yeah.
Second part, well, not so much. Cool. Thanks for asking. I'm gonna have to think about that though.
Yeah. And then problem 75. Um,
In chapter 7.
really easy, but I was wondering if there was like another way to do that.
So how did you get the, I mean, because you can easily get the MGF since they're independent, right? You can easily get the MGF of the sum of the two things, right?
Yeah. So
So like
I
M,
didn't get the well, I got the moment generating function of the sum, but I didn't think I really needed it. So
oh,
I just took the moment generating functions of the individual random variables, and you can just sort of match them up with the distributions that they correspond to.
right. So you just extracted the, oh, okay. So you,
And then I used that to calculate the probability
okay, I see.
for part A, and then the expected value for part C, because they're, I assume, still independent.
Yeah. So
So,
the moment
but I,
generating function of X, was that basically like the Poisson or something?
yeah,
And then the moment generating function for Y, that was
was,
basically uh, binomial or something.
yeah.
Okay.
Um, but I was wondering if there was a way to use the moment generating function.
Yeah,
Like,
that's what I was thinking. So first of all, the moment generating function of the sum is just going to be the product of the moment generating functions, right?
yeah,
And you know that um, Right. So whatever it is, I mean, you know that the probability of x plus y equaling 0. So what do I mean by p0? That is the probability of x plus y equaling 0, correct?
Okay.
Sorry, this shouldn't be t in here. What should this be? It should be e to the t and e to the 2t, yeah, etc. So P1, that's the probability that x plus y equals 1. P2, that's the probability that x plus y equals 2, and so on and so forth. Okay?
Okay.
So how could I get a handle on like these various probabilities? Well, I mean, here's a little trick. So, oops, what am I doing here? So the moment generating function of x plus y of t, let me just rewrite what I had on the previous screen. Whatever it is, we know what it is, right? But we also know that this is going to be, you know, p0 plus p1 e to the t plus p2 e to the 2t plus etc. What if I put t equal to, what if I plugged in t equal to natural logarithm of, you know, the natural logarithm of x or something like that? Okay, what would this turn into?
Each e to the t would turn into an x.
Yeah, so this would be p0 plus p1x plus oops, what am I writing? Plus p2x squared plus etc., right?
Yeah.
So from here you could actually get, you know, if you take the derivative with respect to x, you could pluck off the probabilities one by one. Does that make sense?
Yeah.
One thing that kind of makes me nervous is you want to take the limit as x goes to 0 of this, because technically plugging in x goes to 0 from the right of this, because technically plugging in x equal to 0 into the logarithm is not allowed. Right? But watch this. If I take the derivative with respect to x of this thing, well, on the one hand, this is going to be, I would take m sub x plus y prime with logarithm of x plugged in, but then I would have to multiply by the derivative of what's inside. You see what I'm saying? So I would have to multiply by the derivative of logarithm of x, which is 1 over x. Does that make sense?
Yeah.
Okay. But on the other hand, what would it be equal to? If you just think about this massive polynomial on the right-hand side. If I took the derivative, what would I have?
P sub 1
P
plus
sub
2
1
p sub
plus,
2x.
right? And if I want to keep
Etc.
3 sub 3x squared, etc. Yeah. Okay. And so technically speaking, I could get p sub 1. So like p sub 1 would be equal to, this is kind of what I was talking about at the beginning of the semester, where I kept saying the moment generating function really kind of gives you everything. Like you might not realize it, but you can actually even extract the the various probabilities from that thing. So it'd be like the limit of, you know, x goes to 0 from the right of this thing. Okay. And it's not as if we have to work in total abstraction here, Matthew. I mean, we actually have formulas for the moment generating function of x and the moment generating function of y, correct? So, and by the way, how could I get P2 apparently?
You would just take the second derivative.
Yeah, you would take the second derivative, but you would also have to you would have to divide by, right? Wouldn't I have to divide by
2.
Yeah, so P2 is equal to 1/2 times the limit as x goes to 0 from the right of the second derivative of this thing, mx plus y, with logarithm of x plugged in. Does that make sense? And what
Yeah.
what do you think the formula would be for like P sub k? You care to take a guess?
Would that be 1 over k factorial?
Yeah, 1 over k factorial times the limit
Times,
goes to 0 from the right of the kth derivative of that thing. Yeah.
okay.
So that would be one way to pull it off. Does that make sense? But you cheated. You just said, oh, that's obviously the Poisson and that's obviously the the binomial, right?
Yeah.
But if I would challenge you to go and kind of mess with the derivative. I mean, they only had you go up to 2, right?
Yeah.
Probability that x plus y is 2.
Yeah. I mean, we only need the probability that it's 2, but yeah.
Yeah. So yeah, I would challenge you to use this formula right here and verify that you get the same thing. Because
Okay.
you will. What happens if you plug in t equal to logarithm of x? Oh man, look, that has to be what they expected you to do. If you plug in t equal to logarithm of x into those individual moment generating functions, look how nice they are. Like what happens?
You get e to the 2x minus 2
Yeah, how simple is that?
and 3/4 x
Yeah.
plus 1/4 to the 10th.
Uh-huh. Yeah. So that's pretty nice, right?
Yeah.
And you would multiply those together to get the moment generating function of x plus y. In fact, now I'm super curious, right? So let's see real quick. So the moment generating function of x plus y of logarithm of x is mx logarithm of x times my logarithm of x, since these are independent, right? And what did you say we get? E to the
2x minus 2
times
3/4 x plus 1/4 all to the 10th.
Right. So this is sort of annoying. I'm gonna pull out 3/4, okay? And if I pull out 3/4, it's gonna be raised to the 10th power. Yeah?
Okay.
Okay, and this is gonna be x plus, what would I need to do? If I pulled out 3, it would be x plus,
1/3.
yeah. Okay, and let's take a couple of derivatives of this thing. Well, okay, let's take one derivative at a time here. So first of all, this constant just comes along for the ride. That's just a constant after all. Okay, if I take the first derivative of this, what am I going to get? 3/4 to the 10th. Let's do derivative of the first, which is just 2e to the 2x minus 2 times x plus 1/3 raised to the 10th. And let's put a giant parenthesis around this, right? Because that thing's going to multiply. So the derivative of the first times the second plus the first, which is e to the 2x minus 2 times the derivative of the second, which is 10 x plus a third to the 9th. That's the reason I pulled out the 3/4, by the way. So I wouldn't have to use the chain rule. Does that make sense?
Yeah.
So let's simplify this. Okay, this is 3/4 of, so first of all, I can pull out, let's pull out everything we possibly can. Okay, I can pull out, of course, the 3/4 is still here. I can also pull out 2.
Pull out an x plus 1/3 to the 9.
Yeah. And I can pull out
E to the 2x minus 2.
And what's going to be left behind? Man.
X plus 1/3 plus 5.
X plus 1/3 plus 5. We're going to take the second derivative of that disaster. That's sort of annoying, but and then we'd want to take the second derivative of that, and then we would want to, okay, let's just do it. What's that going to be equal to?
3/4 to the 10th times 2.
Okay, and you would have to use like the triple product rule or something, right? So, oh right, times 2. Times what?
Times 9 times x plus 1/3 to the 8th. Times the rest of it.
Times e to the 2x minus 2. Times, what is that? X plus 1/3 plus 5. That's like x plus 16/3, right?
Yeah.
Plus?
2 times.
Well, 2's outside. Oh, right. Yeah.
Yeah.
2 times
X plus 1/3 to the 9th. E to the 2x minus 2 times x plus 16/3.
Okay, plus what?
X plus 1/3 to the 9th. E to the 2x minus 2 times 1.
And what do we need to plug in here?
Zero.
Yeah. So what do we get? That's amazing. And we need to plug in 0 and divide by, right? Because remember, P2 is equal to that divided by 2. That just gets rid of that first 2, correct?
Yeah.
So what's P2 going to be?
3/4 to the 10th times the quantity 9 times 1/3 to the 8th times e to the negative 2 times 16/3 plus 2 times 1/3 to the 9th e to the negative 2 times 16/3 plus 1/3 to the 9th e to the negative 2.
Okay, is there some way we could simplify that?
You can factor out an e to the negative 2 and a 1/3 to the ninth.
1/3 to the ninth or 1/3 to the eighth?
Well, you have 1/3 to the eighth, but then it's multiplied by 16 over 3.
Ah, okay. So what's P2 going to be then? Help me out here. So P2 is going to be
3/4 to the 10th times 1/3 to the ninth, e to the negative 2. 9 times 16 plus 32 over 3. Plus 1.
Man, is that the same answer?
Um,
What does that number end up being? 9 times 16.
I don't know, I type mine into Excel. It ends up being really small.
Okay, so hang on. So P2, let's do this. So 9 times 16. Okay, can you do that fraction? So
9 times 16 is 144.
9 times 16 is 144.
Yeah, so you get 144 plus, 432 plus 32
Right,
plus
because you
3, so you
multiply
get 467 over 3.
over 3.
Yeah,
And then
well, is what you're multiplying it by, then you have all the other stuff.
actually all the 3's cancel
Yeah,
because it's 3/4 to the 10th. And then it's times 1/3 to the 9th. And then it's times e to the minus 2. So like all the 3's cancel, right?
yeah.
So what do we have? It's the P2 ends up being
467 over 1/4 to the 10th times e to the negative 2.
467 over 4 to the 10th times e squared. So is that what you got before?
I'm not sure. I can try typing it into Excel.
Okay. Before you probably just had some kind of decimal, right?
Yeah.
Do you know how to do e squared?
Yeah, it's just EXP.
Yeah.
Yep, it works.
Well, that's kind of satisfying. So there you go. It worked. Okay. Well, cool. Thanks for coming with some good questions. You always come with good ones.
All right. Thank you.
All right, is that it?
Yeah.
All right. Thanks a lot, Matthew. See you later.